chapter 2, and that's fine. We'll get through all the major stuff that we need to, but if there's any little like points on like, say, that exam review that you're like, we didn't talk about that, well, then I'm not going to ask you any questions on it, okay? So the questions that you'll have will be based on material that's covered in class. If you didn't grab a 4x6 note card, make sure that you get one on your way out. Remember that you can fill out anything on one side, whatever notes you want to put, bring that with you on Monday night to take the exam, okay? So you have sort of, like, think of it as like a cheat sheet that you can prepare. Anything you want to write on one side, if you can write really, really small, you can put a lot of information. You'd be surprised, like, how much information I have gotten on these cards. I'm like, wow. Like, I mean, they like write like tiny little handwriting and like put tons of information on it, which really like makes it a whole lot easier. All right, so in this, we started last time, we just started talking about chapter 1 and just really introduced this idea that there are subatomic particles in an atom. Protons, neutrons, and electrons. Protons, neutrons, and electrons, they differ by size, they differ by location, and they differ by charge. So you should be able to identify like the size, location, and charge for each of them. Protons and neutrons in the nucleus, electrons outside. Protons and neutrons have mass. Electrons have mass that's so small, you can consider it to be like negligible because it's 2,000 times smaller than a proton or a neutron, so it's not going to add mass to the atom itself. And then the charge is the other difference. Electrons are negative, protons are positive, neutrons are neutral. So if we look at this one down at the bottom, that's a lithium atom. So if you look at lithium on the periodic table, its atomic number is 3, so it's the second just below hydrogen. So that number 3 actually tells you information about lithium. If you look at the number underneath it, 6.941 on that periodic table. If you're looking at your laminated periodic table, they round it a little more. Well, it's 6.941. And so in that one, that number is also going to tell us information. These two numbers you can use to determine the numbers of protons, neutrons, and electrons in an atom. So they started off with carbon. They said, okay, well, kind of like with density, we said water ended up being like the standard. Water has a density of 1 gram per mil. Well, we're going to make our standard carbon. So if we have one single carbon atom, they said it has a mass of 12 atomic mass units. So AMU, that stands for atomic mass units. It's not a gram. It's not a mass measurement. It's really considered kind of like a relative mass. We're going to say that protons and neutrons each weigh 1. They have 1 AMU, which is atomic mass unit, and it's right here. So there's, oh, I didn't know it was going to color it behind. There's the atomic mass unit, or AMU. It's really just a way to be able to do counting when we're talking about protons and neutrons, and they're so small. We don't want to have 1 times 10 to the minus 23rd. Instead, it allows us just to have everything kind of on a standard of 1. Protons and neutrons have a mass of 1 each. Electrons have a mass of 0. So we can identify by looking at the number above each element. It's the whole number on the periodic table. They call this the atomic number. So this atomic number was assigned because it really defines the element. The atomic number tells you the number of protons. In a neutral atom, because like if you had an atom of carbon or an atom of nitrogen or an atom of oxygen, they're neutral, which means that the number of positive protons has to equal the number of negative electrons. So if we know that positive protons equals the negative electrons in a neutral atom, then the atomic number tells you the number of protons and the number of electrons. So if I look at the periodic table and I just look at like lithium, Li, 3 is above, okay? That 3 is the atomic number, and that tells me that there are 3 protons and 3 electrons in each atom of lithium. If I look at carbon, carbon is 6. That tells me there's 6 protons and 6 electrons in 1 atom of carbon. So you don't even have to do any math with that. It just tells you. So the only other question is neutrons. So how do you figure out how many neutrons? So you remember protons and neutrons give the atom mass. Electrons basically have a mass of 0. So the atomic mass is the number that's below. So in lithium, it's 6.941. So this is the atomic mass. So it's basically telling you the number of protons and neutrons. So take the atomic mass, just round it to a whole number, subtract the atomic number, and that will tell you numbers of neutrons. So in lithium, I would take 6.941. I would just round that to 7. I would then subtract 3. That tells me that lithium has 4 neutrons. So carbon is 12.01. So how many protons does carbon have? So if this is, look at carbon on the periodic table. Its atomic number is 6. Its atomic mass is 12.01. So how many protons does it have? 6. And you know that just from the number above. Okay. How many electrons does it have? 6, because that's the number above. So then, to figure out numbers of neutrons, what do? Take 12.01, round it to just 12, subtract 6. That tells you that there's 6 neutrons. So you do have to do the math with the neutrons. You have to take the atomic mass minus the atomic number to figure out numbers of neutrons. For protons and electrons, you don't have to do any math. Just remember that the number, atomic number, the whole number above the element symbol, that tells you the number of protons and the number of electrons.
Is the symbol for neutrons a little circle?
That's the little n. Remember, so they use a little 0 to show it has no charge.
Okay.
P is plus, E is negative, N will have a little 0, just as a way of denoting that it has no charge. So we can do some of these. So in this first one, there's Ag, Th, Hg, Na, Kr, and Zn. So in each one, use the periodic table to determine how many protons, how many neutrons, how many electrons in each one. How many protons, how many neutrons, how many electrons. And this really should be a little e. Mm-hmm.
Maybe it's just me, but when you said, I asked you that question about which 20, the periodic table.
Mm-hmm.
Okay, so when you say learn the first 20,
Mm-hmm.
that means,
The first 20 according to atomic number.
okay, so,
Hydrogen is 1,
yeah,
helium is 2. Go all the way across, the helium is 2.
okay,
Now go to the next row, lithium is 3. Beryllium is 4. Boron is 5. Carbon is 6. See the whole number at the top? That's the
Yes.
atomic number.
okay,
So you learn the first 20 according to that whole number.
okay,
All the way to calcium. See calcium's 20?
20,
Mhm.
okay.
So you need to know the names and the symbols for those 1 through 20.
And then you gave us.
And then I gave you 10 more on that page with the periodic table. The
Okay.
ones like chromium, iron, copper, zinc,
Yes,
mercury, silver, lead,
Okay.
those ones. So I
Okay.
added like those 10. But
okay,
when I say elements 1 through 20, we number them. And if you follow across, you see that that number increases as you go left to right.
yes, okay.
Okay.
I was looking at the red numbers.
Yeah, so the red numbers, that's in here. So in this, The trick in doing these, like you don't have to memorize the number of protons, neutrons, and electrons. You just have to remember how to solve for this. So when you look at Ag, okay, find Ag on the periodic table. First off, what is that? Because that's one of the ones you're supposed to know. What is the symbol? Ag stands for silver. So this is silver. Okay, so I know this is silver. When I look at Ag, do you see that it's Ag? 47 above and below is 107.9. So you see that on the periodic table. Okay, so how many protons does it have? 47. The number at the top tells you the number of protons. Don't have to do any math, just have to remember. Because atoms are neutral, the number of positive protons equals the number of negative electrons. So it also has how many electrons? 47. So those are the same. Okay? So the atomic number tells you numbers of protons and numbers of electrons. Now, how do I figure out numbers of neutrons? 108 minus 47. So you take the atomic mass, round it to a whole number, and subtract the atomic number. So you're basically just subtracting the two numbers, just the number with the decimal, just round. If it's less than 0.5, round down. If it's more than 0.5, round up. So when I do that, 108 minus 47, 61. You will always have a periodic table. So now with this, you can tell me the numbers of protons, neutrons, and electrons in any atom on the periodic table. But if I ask you the name, it's only those 30 that I gave you in the list that I would expect you to know the name and the symbol. Okay? But I could give you the symbol for one you've never heard of, like indium, which is 49. If I asked you IN, it wouldn't matter. I wouldn't ask you the name, but you should still be able to tell me protons, neutrons, and electrons. You're going to do this exact same thing. So just practice these 5. Make sure that you feel like, okay, I can do that, because they're not terrible, but any of the ones that you're supposed to know, you should be able to tell me the name of it as well.
Did this table like ever change, like every
Nope.
couple years?
Nope. No. In fact, my laminated copy doesn't have the actual names that have been agreed upon. They have found all of the elements up through 118. But if you look at mine, see how I have a couple of blanks? And I also have one from 112 up don't have names. They're like unknown B, unknown Q. And it's just because the Americans and the Europeans hadn't gotten together to agree. So they have since gotten together and agreed what the names of those symbols, those elements are. Well, and the big problem is those elements that are white, remember, those are the ones that are unstable, and as soon as you make them, they break down. So that's why, see their atomic mass is in parentheses? That is because it's kind of like, that's the atomic mass like when they make it, but as soon as they make it, they break it down. It breaks down. It's not very stable. It's kind of what we're going to talk about in this chapter 2 stuff. So if I asked you TH, I would not expect you to know the name of TH, because TH is its atomic number is 90. And it's not one of the ones I told you needed to know. I will tell you that TH is thorium, but I would not ask you that. You just have to know the names and the symbols for elements, those 1 through 20 and those extra 10. But if you see TH, you can scour the periodic table. See, it's the very bottom row all the way on the far left is TH. So looking at that, I know that I have 90 protons because its atomic number is 90, which means it also has 90 electrons. And then to find the number of neutrons, I take 232 and subtract 90. So that gives me 142 neutrons. Pretty big compared to hydrogen and carbon. Hg, though, I might ask you what the name of this is, because it is what? This is one of the ones that you needed to know, right? So that's mercury. So then you got to find Hg on your periodic table. How many protons? 80, which also means that I have 80 electrons. Protons and electrons are the same. Then I look at 200.6 minus 80. At 200.6 rounds to what? 201. Oh my God. And it does this. Okay, so 201 minus 80 is 121. It's 121 neutrons. Just subtract atomic mass minus atomic number. So Na, if you see Na, you should know that it is sodium. You should be able to tell me the name. Protons, it has 11 electrons. They're exactly the same. Then I take 22.99 and do what? Round it to 23. Subtract the 11. Tells me that I have 12 neutrons. Kr is not one you would need to know, but it's krypton. Superman's weakness. Finding it, it's all the way on the very far right column. Fourth one down. It has how many protons? 36. 36 electrons. And then how many neutrons? So 84. I'd round 83.8 to 84. Subtract 36 gives me 48 neutrons. All right. Last one you should know. This one is zinc. Z-I-N-C. Finding it. How many protons? 30. Which means it's also 30 electrons. Then if you find zinc at 65.39, so I would round that to, 65.39, so it becomes 65 and subtract 30. 35 neutrons. So see, they're all the same. The only thing that's different is the ones that you have to know the names and symbols, then I might ask you the name as well. All right, so you can see that this would be a couple of questions. Pretty easy though, as long as you remember how to use a periodic table, right? And like I said, if that's something that you get like, oh, I don't know if I'm gonna be able to remember this, put it on your note card. Draw one example and be like atomic number, number of protons, number of electrons, atomic mass, subtract to equal number of neutrons. Put that in really small letters on your little note card so you don't mix them up. Okay?
Would they ever be more neutrons than protons and electrons?
Yes. Well, it is. Didn't you see here? Look at Mercury. Mercury's got 121 neutrons. Oh, nope. Not. In fact, the bigger the atom is, the more neutrons you tend to find compared to protons. So notice like Mercury is 80 and has 50% more neutrons. But like looking at sodium, there's 11 protons, only 12 neutrons. Smaller atoms tend to have almost equal or closer to equal number of neutrons. But when you start getting big, like look at thorium. So thorium has 90 protons, but 142 neutrons. That's a lot of neutrons comparatively. And that actually makes the atom less stable. So that's why those ones that are in white, those are really big atoms. They have a lot of neutrons and they're not very stable. Okay? All right. So I ended up not. I need to get rid of that because it looks odd. So there was a couple of other ways that they decided to start writing these. I did not make these rules. I promise. I promise that I didn't make these rules. But it ends up being an issue is they said, well, we can like shorten this, okay? So we can, if we're looking at just one atom of any element, we can list it with a single mass number without the decimal places to show an easier way to figure out numbers of protons, neutrons, and electrons. So they took carbon and they wrote it this way. So how does this look different than what you see on the periodic table? Yes. Yeah, like who decided that was a good idea? Like if they should have kept them the same, but no. So you got to remember the bigger number is the mass. The smaller number is the atomic number. Okay? The atomic number will always be a single number. Atomic mass, when it's written this way, they call this symbolic notation. It is just a way of being able to describe an element its atomic number and what they call its mass number. So you know its mass number is protons and neutrons. The atomic number is protons and also electrons, right? Just because it's neutral, so it's electrons as well. So in this, you can see there's 6 protons, 6 electrons. You can also subtract 12 minus 6 and figure out that there's 6 neutrons. So for example, iodine. If I had iodine 53 and 131, looking at that, how many protons? 53. How many electrons? 53. And how many neutrons? 78. So just do the math, right? Just like we did before. But just remember, in this example, just remember in this, if you see it, it's always the bigger numbers, always the atomic mass. Okay? The smaller numbers, always the atomic number when we're talking about this. So there's one other way you might see these written. So you might also see this written as, why is this acting like ridiculous tonight? So you might also see this written as carbon 12. So this is kind of like a third. So you might have it the way it's on the periodic table, just looking at the periodic table. You might have it written in this symbolic notation, or you might have the name of the element dash with a number. So what does that 12 tell you? That's the atomic mass. So if it's carbon, you know that carbon has what atomic number? 6. And that's not going to change. The atomic number defines that carbon has 6. 6 protons is what makes carbon kind of like behave the way it does. Just like iodine would always have an atomic number of 53. Okay? So that's why they could write carbon 12, telling you carbon with a mass of 12. So those are kind of the only 3 ways that you'll see it. I just don't want that to throw you, especially if you're doing the homework and going through and you see them written in these different formats. It's really the same. You can still use your periodic table. You can still figure out numbers of protons, neutrons, and electrons with all of them. It's just different formats. So they found that there are atoms of carbon that have a mass of 12, but they also found that there's atoms of carbon that have a mass of 13, and even a very, very small number of carbon atoms that have a mass of 14. But they're all carbon. So if they're carbon, then you know that they have how many protons and electrons? 6, right? So we know that all have 6 protons. They all have 6 electrons if they're neutral, equal numbers. So carbon 12 has to have 6 neutrons. So what does carbon 13 have? If it has 6 protons, 6 electrons, then it must have how many neutrons? 7, right? So 13 minus 6 would be 7. So then carbon 14 has to have 8. So these still act like carbon. They just have different numbers of neutrons. They call elements with different mass numbers isotopes. So you can recognize them this way. So like carbon 12, carbon 13, carbon 14. I could also write it in that symbolic notation. So it would be like this: C with a 12 and a 6, C with a 13 and a 6, and C with a 14 and a 6. So notice they still all have 6. They still all have 6 protons and 6 electrons, but they have different mass numbers because they have different numbers of neutrons. So we can write them in either format. So the amount of each of these found in nature is the reason that the atomic mass on the periodic table is the way it is. So notice when you look at carbon, see it's on that one it's 12.0108. Okay, so it's not a whole number, it's got those decimals. So what they did, and let me blow this up just so that you can see it a little bit better in a zoom. So what they found is they said, okay, so carbon 12, 99% of carbon atoms are carbon 12, which means they have 6 protons and 6 neutrons. They'd have a mass of 12. There's a really small amount, just under 1%, are carbon 13. And even less, way less than 1%, are carbon 14. But because of that, if I find the average mass, that's the relative mass compared to the different isotopes, that's why carbon has a mass of 12.01. So that's the reason why the periodic table has those numbers after. It is because there are atoms of the same element, they have the same number of protons and electrons, but they differ by numbers of neutrons. And so the periodic table is showing you like an average mass compared to their abundance. So since 99% of the carbon atoms found are carbon 12, that's why the atomic mass is 12.01, really close to 12. So when I look at the periodic table, I kind of know what the most common isotope is just by looking at the number it's closest to. So like if you look at oxygen, so oxygen's 15.9994. So you would say the most common isotope of oxygen is going to have 16. Right, if I just rounded it to a whole number. But there might be some oxygen 15, there might be some oxygen 14, and that's the reason why those numbers are a little bit less. So that's where that comes from. That's why the periodic table like ends up with that decimal place. But for us, we're just going to round it to a whole number and find the most common isotope numbers of protons, neutrons, and electrons. So they just say that atomic mass on the periodic table, it's the average mass based on abundance, the most common ones. And most of them, if you look, you notice they're pretty close to a number. They're pretty close to one number or another, where you're just rounding up a little or rounding down. Like oxygen on yours is 16 because it's been rounded up that much. Fluorine, 19. Okay, so what about these isotopes? So this, radiation chemistry, is one of the newest branches of chemistry in existence. It's only about 125 years old. So Henri Becquerel, French guy, so he was actually studying new metals, new earth elements that were found, and he had a sample of rock that he kept in his lab. And so one common thing when doing all of your characterization of different types of soils, metals, rocks, that you'd have to take photographs. This is back in the day, no digital. This is back when they had like the old-timey like photographic plates. Remember the guy that used to like get behind the little covered curtain and had like the big box? So that's the kind of like photographs that they were taking back then. So he had photography film in the lab, and he had this rock soil sample next to it. He went to develop that film, and the film was completely white. So it would be completely white if it was completely exposed. Like if you took regular photography film and you exposed it, when you developed it, it would just come out white. Like it had been shined with a really bright light on it, it would expose it. So he thought something was wrong with the film, sent off and got more film, same thing happened. Then he was like, well, this can't be a coincidence. There might be something, I think there's something in this room that is actually exposing my film. So then he did an experiment. So he took photography film and he put it in different places all over the lab. And he found that film that was close to this rock sample was exposed more than film that was further away. So he eventually actually said, it's this material is actually exposing, it is releasing radiation. So I always think of radiation from the sun as like the warmth, the sunlight. So he's saying, no, this is coming from a substance. This isn't coming from the sun, that there is atoms that are releasing energy, and that energy is exposing the film. So he kind of coined the term radiation. So nuclear radiation is energy that's coming from atoms. elements that emit or release this kind of radiation, they call them radioactive. So that's where that term comes from. It's just a way of describing substances that release nuclear radiation. And isotopes, elements that have weird numbers of neutrons typically, they are less stable, and they get more stable by breaking down. And when they do, they release this energy. So he had a sample of something that was radioactive, that was emitting nuclear radiation, didn't even know it, sitting on the lab bench next to him, and eventually came to figure this out almost like just as an aside, because it was exposing his film in the lab. He didn't have any other way of being able to measure it. So decay, I always think of things when they decay, they like rot, right? They break down. So radioactive decay is the breakdown of unstable atoms, trying to become more stable. And when they do that, they release energy. So what atoms on the periodic table do this? What elements? There's a number of different elements that have radioactive isotopes. Big ones, large atoms, okay? So the ones, remember, like we looked at thorium. So thorium's got like 140 neutrons, really big. Those that are larger than atomic number 83, so if you find 83 is bismuth, which is Bi. If you look past, so see, it's like the 4 columns in from the right is Bi, and then Po. Once you get to polonium, which is Po, and then At is astatine, Rn is radon. You don't have to know any of those. But look at their atomic masses. Do you see the atomic masses are in parentheses? So the atomic mass, when you see it in parentheses, you know that means it's not a very stable atom as a whole, and it tends to break down. So that's why they don't have a lot of isotopes of this, because it's there, but it's in the process of breaking down. So it's kind of hard to measure all the different isotopes when it doesn't hang around but so long. So really large atoms, or atoms that have a lot of neutrons. The proton-neutron ratio is important. If you have more than twice the number of neutrons compared to protons, then you see it's unstable. So those are kind of like, not all elements are radioactive, not all isotopes are radioactive, but ones that are really big and ones that have a lot of neutrons. Those are really kind of the more common ones. The ones we're going to talk about tonight are these 3. So we're really not going to talk about the positron and the neutron types because they're not as commonly used in medicine. We're going to talk about these 3 and then kind of like how they're used in medicine and when you might be exposed to alpha, beta, or gamma radiation, and then how you protect yourself. Because whether you're thinking about going into veterinary science, dental hygiene, or into nursing, all of those, you are going to end up either having to take patients to go have an x-ray, or being in the room while a patient's having an x-ray, or having to have patients that are treated by radiation for cancer. Same thing. Sometimes it's external, sometimes it's internal. So there's all of those possible exposures. So that's really the reason to cover this in this chapter. So in this, and I will tell you with these, I'm not going to ask you to complete the reaction, but I do want you to be able to recognize the 3 different forms of decay that occur. And I'll tell you how you can tell. So this first one, the first one's called alpha decay. And in alpha decay, an atom, the nucleus of an atom that's unstable breaks down. And in doing so, it actually spits out a helium nucleus. So it's going to spit out 2 protons and 2 neutrons. So it'll lose a mass of 4, and it's going to drop a proton number, atomic number will decrease by 2. So if I start with uranium-238, and it undergoes alpha decay, what will its mass be? It goes from 238 to what? To 234. So the atomic mass will decrease by 4 because there's the 4 at the top. So this would be 234. the atomic number, since it spits out 2 protons, the atomic number will decrease by 2. So from 92, it's now 90. So the top number drops by 4, the bottom number drops by 2. But now if it's got atomic number 90, find uranium on the periodic table. So uranium is in the very bottom row. See that it has atomic number 92? Now it's atomic number 90. It's not uranium. What is it? Thorium. It's TH. So do you see that as that if the atomic number decreases, then the symbol changes? So the next one, so this one's californium, CF. So it's 257. If it undergoes alpha decay, what happens? So the mass goes from 257 to 253. It's going to go down by 4. The atomic number goes from 98 to 96. Now find 96 on the periodic table. Do you see CM? That's curium, named after Marie Curie. So alpha, it's going to make the whole nucleus is going to get smaller because 4 particles get pushed out of the nucleus, and that's going to help to decrease the size of that nucleus and help to make it a little more stable. So how do you recognize this? Look for this. If you see He, a helium nucleus, as a product, you know it's alpha decay. So the helium nucleus is a product. So if you see that, you know it's alpha. So if you see a helium nucleus, so it'd be He with the 4 and the 2, and it's got a +2 charge, then you know it's alpha decay, because none of the others have that. Okay? So then beta. So what happens in beta decay is you have a neutron in the nucleus of an atom, and it actually splits in half and forms a proton and an electron. The electron comes out because electrons circle the nucleus. So the electron comes out of the nucleus. But it leaves the proton behind. So really, think of it, it's like a neutron gets converted to a proton. Because remember I said a lot of neutrons makes it unstable. So we're just going to take the neutron, convert it to a proton. That'll help to decrease the number of neutrons. So if a neutron has a mass of 1, it gets converted to a proton that has a mass of 1. This is why the mass doesn't change. So there's no change in the mass. So see why that's got a 0? It's got the little E with the little 0. But the atomic number is going to increase by 1. That's where that number comes from. So if I start with carbon 14, so it's carbon with those extra neutrons is less stable. Carbon 14 undergoes beta decay. What happens to the mass? So it stays 14. So what happens to the atomic number? To what? 7. So if it's an atomic number is 7, it's not carbon. Now what is it? What's the element? If it's atomic number 7, it is nitrogen. So do you see that? Look at the atomic mass of nitrogen. The atomic mass of nitrogen on the periodic table is 14. So what is it here? 14. It's a whole lot more stable. So nitrogen with an atomic mass of 14 is a lot more stable than carbon with an atomic mass of 14. So undergoing this beta decay allows it to convert to an atom that has more equal numbers of protons and neutrons, and that's going to make a more stable atom. Okay, so let's try the last one. So the last one's copper, Cu. 66. If If it undergoes beta decay, what does it make? What's the new mass? Doesn't change, right? And then the atomic number becomes a 30. So now it's not copper, now it's what? Zinc. So look on your periodic table. Do you see 30? Find atomic number 30. Do you see that it's zinc, Zn? Okay, much closer. So now this one is going to have 30 protons and it's going to have 36 neutrons, much more stable than what the copper was. So by doing that conversion, you can think like that the nucleus gets like a little more stable each time. But this is really the way to identify beta. So if you see this electron with a 0 and a -1, then you know it's beta decay. In order to identify beta decay, look for that electron being a product. So the electron will always be a product in this reaction. It gets shot out of the nucleus. So then the third. So the last one is called gamma decay. Gamma decay is the highest energy. There is no particles released. There is no change in mass, no change in atomic number, no change in symbol. It's just a lot of energy. So it's just like radiation energy coming out of an atom that's breaking down, but there's no particles. So what happens to the atomic mass? Stays the same. So this is Pu. Pu is plutonium. So plutonium, when it undergoes gamma decay, the atomic mass doesn't change. The atomic number doesn't change. The element doesn't change. So there's no change. I think of gamma decay as being like, it's when protons and neutrons like shift around inside of an atom where there's a lot of protons and neutrons. Because plutonium has 94. So plutonium's in that bottom row. See that it's actually in the white because it doesn't last very long. Plutonium automatically starts breaking down because it's such a big atom. It has 250 protons and neutrons. So you can think of like trying to cram them into a really small space. That's why they're so unstable. So what they like to use is they use the Greek symbol gamma. So my Greek symbol and the Greek symbol is, they look a little different. It should look like that. I just always end up drawing it looking kind of like an 8 without the cross on the top. I kind of draw it looking sort of like that. I guess you could kind of put a little thingy on it like this. I don't know. But that's what their gamma symbol looks like. So just remember, gamma is literally like just the energy. See how that looks? And you'll see that it'll have the little gamma symbol with a 0 and a 0, showing you that there's no change in mass, no change in atomic number. And you'll see that the product and reactants are the same thing. They look like they're the same. This just represents this energy that's being released. All right, so like in this one, if you see this on a test, you'll get the entire chemical reaction. So I won't like ask you to finish it. So you would see 218, 86, and then it would have Rn. So you would see this. But seeing that He, this is the one that tells you this is what? This is alpha. Right? No matter what the reactant and products are, you'll always have that He. So that's an easy way to identify it. Second one, you would see 42 and 20 and Ca. Atomic mass doesn't change, atomic number goes up, it's a different formula. So you'll see, no matter what the reactant and products, you're always going to see that E with the 0 and the -1, and this is what? Beta. And then with the last one, you may see this, and it would look like this. And so see the little gamma symbol. So this symbol with the 0 and the 0, that's going to tell you that it's gamma decay. Sometimes they'll put like a little asterisk on the reactant to show that it has higher energy than the product. But that's really what the little asterisk is, just showing like that atom is losing some energy. So the asterisk doesn't really mean anything, but that's not an uncommon way of trying to show that there's energy released. And you would see it like on the reactant side. It's just showing that it's releasing this energy. Okay? But you would get this whole thing. Okay? You get the whole reaction, and I would just ask you, what type of decay is this? So seeing the electron tells you it's beta. Seeing the hydrogen or the helium nucleus tells you it's alpha. And having the funny little squiggly thing, that's the gamma. Okay? So related term is X-rays. X-rays are really the most like gamma rays. They have energy very similar to gamma, but X-rays do not actually use a radioactive substance. An X-ray is produced when a beam of electrons, which is really like electricity, a beam of electrons bounce off of or hit a metal. The most common metal they use is tungsten. So tungsten is the typical metal that's used in generating an X-ray. So when energy hits a metal, that metal becomes energized. And when it releases that energy, that's an X-ray. These energy waves are strong enough that they can pass through soft tissues of the body. So if you have somebody, the really strange looking appendage, and you do an X-ray, if there is injury, that'll show up because bone is solid. Muscle, skin, subcutaneous tissue, arteries, vessels, those are soft. And so the waves pass straight through soft tissues, but they get blocked by bone and hard tissues. So that is how you do an X-ray. So if you think that you've got an injury, you go, now it's all digital. So they have a digital film that captures this energy. So you lay your arm, they put the film underneath, and then that energy is exposed. Anything soft, the X-ray passes straight through and exposes the film. But the bone is going to block the energy, and that then creates the outline of your bone, the outline of the hard tissues that they're looking at. When they do a CT scan or a CAT scan is what they used to call it, now they call them CT scans. A CT scan is just taking X-rays from lots of different angles, and it puts it together in a three-dimensional view. So that's why it's more helpful, because you can think like you can look at the bone from this angle, from this angle, from this angle, from this angle, instead of just like a flat view, which is what a single X-ray does. Digital X-rays have like really revolutionized how much energy you get exposed to when you have an X-ray done, and like how easy you can like take a digital X-ray and you can like adjust the contrast so that you can make the shadows more obvious. It used to be really difficult to see, but now you can like lighten and darken, you can change the brightness on an X-ray and be able to pick up stuff that you were never able to pick up before. So a CT scan is really just a 3D X-ray. But that's all it's doing, is this energy, it's a lot like a gamma ray, passes through soft tissue but gets blocked by bone and exposes a film. But this doesn't really do very much for somebody if like they're trying to look inside your head, right? Because then the skull is this block, okay? Trying to look at like the chest. You've got the ribs. You have ribs in front, ribs in back, the vertebral column, the sternum. So there can be challenges in trying to get an X-ray and be able to see like soft tissues underneath bone. So that is still an issue. Having a CAT scan, having the CT scans really does help. So energy, this energy, whether we're talking about alpha, beta, or gamma, energy from these types of atoms has the ability to cause damage. It has the ability to change the reactivity of molecules, and these can be molecules that are in living cells. So you can come up with ideas, okay, well, what kind of energy, what kind of problems can you have? So if you're exposed to radiation, that might make molecules more reactive inside of your cells, or it might make those molecules less active inside of your cells, or it may end up affecting how fast those cells grow, right? And so uncontrolled cell growth is a characteristic of what? Cells that grow without control. Cancer, right? So your concern about exposure to this radiation is that as a healthcare worker, you may be exposed to this energy that might cause molecules in your body to work faster or slower or work abnormally. And so you really want to do what they call shielding, right? So the goal is you always want to limit your exposure, but still be able to do your job. And knowing the form of radiation can really help. So in alpha, beta, and gamma, and we'll say gamma and X-rays are about the same in terms of energy. The rule of thumb is the bigger the particle released from the nucleus, the slower it moves and the easier it is to block. So alpha decay, if a
So like when you have patients, like so when you're doing an X-ray on a person, do they get exposed to the radiation?
Yep.
So like
Both the patient and the person, both the patient and the healthcare worker, anybody that is in that space is going to have some exposure.
so how much can a person be exposed to?
Okay, well, hold on, we'll get there. But first this idea that not all radiation is the same, okay? Not all radiation affects you the same. Not all radiation penetrates through layers of the body the same. Alpha, you can block with a piece of paper, okay? So alpha really only goes about 3 inches or so from its source. So if you add an alpha decaying radioactive substance, if you stay this far away, you're good because it doesn't go very far. Or you could just most of the time they'll take like a piece of aluminum foil and like cover it, and that's blocked, okay? So there's really very little. So alpha is what I would say the least penetrating, and you can block with paper. If you're exposed to alpha and alpha comes up really close to you, like less than 3 inches, it's only going to affect the very top layers of the skin. If it's external, okay? So if it was like right up next to you, it's not going to affect but just the very top layers. It can't pass through all the layers of the epidermis. But beta can actually penetrate through the top layers of the skin and go down into the layers of the dermis. So if you've had A&P, remember the top layer is that layer that's constantly growing. So beta can like penetrate this top layer just into the layers underneath. Okay, so beta, it can penetrate further, like all the way down into the area they call the dermis, which is under the epidermis. So in this, it can also penetrate inches, like about a foot. So it can go further than what alpha can. Alpha can only go a couple of inches. Beta can pass a foot or so. So, but beta, typically what they use is they block this with either like heavy duty aluminum, or they'll use what they call plexiglass. So you know, like at the Hurricanes hockey game, you know the glass that they use to like, so the puck doesn't kill anybody? So that, it's usually about a 1/2 inch thick, it's plexiglass. So that's a common one to use. So they'll block with plexiglass, or really thick foil, like that heavy duty foil, not like regular cheap aluminum foil, but the thick stuff, that's enough to block, so it can't get through. So again, you could cover and close. We used to use beta emitting stuff in grad school, and we would always keep it behind a plexiglass screen, and it was always stored in a plexiglass box. So that way, you're not exposed to it just being in the room with it or walking past it type of thing. Gamma is the highest energy. Remember, gamma doesn't release any particles. So the more particles, the bigger the particles, the shorter it goes. The bigger the particle, the less effect it has. The smaller the particle, the more effect it has. So gamma rays and X-rays, they can pass through soft tissue. So these have the highest amount of energy. They can pass through soft tissue, which means as they go through, they can be hitting any molecules on their way. So if the energy from gamma waves can cause changes in cells all through the area that's exposed. So to block this, you need lead. Oh, and it can travel yards, a couple of meters. Like we're going metric, we should really say meters. I think it's like 3 meters, which is like about 10 feet. So if you're going to block this, you're going to use lead and concrete. So it really does depend on what type of decay the radioactive substance is undergoing. That really depends on how you have to protect yourself. So here it shows like a few centimeters, a couple of meters, but gamma, look, it can go like quite a distance. X-rays go a couple of meters, penetrating, then shows some of that shielding that you can use. So protection, when thinking about shielding, if you're working around radioactive substances, you typically wear like a lab coat, you may wear gloves, you may have goggles on, so that's just going to help to kind of physically protect you from anything alpha. If you're beta as well, it'll end up like, if you have like, most lab coats are kind of like a thick cotton, most of your scrubs, they're not super thin, they're heavier duty. Those will help protect you from exposure. But if you have to work around gamma rays or you have to work around X-rays, this is where you end up having lead shields. Okay, so they have like a body shield. So like if you're a vet tech now, like if you got to take an X-ray of a dog, you can't just say, okay, hold still and go away, because the dog will jump up and run off, right? So you've got to actually stay in there. So vet techs actually have to stay with the animal through any kind of X-ray series that they need to have. So the X-ray tech has to wear a lead apron. So the apron like flips up over their shoulders. It comes all the way down to here, okay? They also wear a little lead collar, okay? Or they have an apron where the collar kind of comes up, which is very uncoordinated because you feel like the thing's like touching all the time. And this is because the shielding that you use, you always want to protect the pelvis. What's in the pelvis that could potentially be a problem? Reproductive organs, okay? So ovaries and testes, because if they get damaged, then offspring may end up with malformations, may end up with you may have offsprings that have problems. So that's why if you're patient, even if it's a guy, you always ask, you're like, are you pregnant? And they're, if it's a guy, you still put the lead apron on because you want to protect the testes. You want to make sure that there's no sex cells that might potentially be damaged by that radiation. Females, same thing. So either way, everybody always gets the little lead shield over the waist. But for a vet tech or for somebody like that has to be in the room, somebody that's working with a patient undergoing radiation treatment, they want to have larger scale protection. So they are typically going to wear a lead shield that covers their torso just to try and protect those vital organs, because they're not exposed like once a year. They're not exposed like once a week. Oftentimes they're exposed to multiple X-rays over the course of the day, okay? Just by taking care of the patients that they're taking care of. So to monitor that, the other thing that you should have If you are doing more than being in the room with more than one x-ray a day, then you have to have a film badge. A film badge is just this little clip that you wear, and it monitors how much energy you're exposed to over a period of time. So most of the time you wear your film badge for a month, and then they ship it off and they give you a new one. And so that film badge will say, you've been exposed to this much radiation over this month. And that's going to make sure that you're not exposed to more than what is safe. So what's really crazy is just how much you used to be exposed to. So when thinking about like, well, how much am I exposed to? You're actually exposed to radiation just going outside. So there is actually what they call cosmic rays. There's rays from outer space, from the sun, from other suns that actually reach the earth and pass through the levels of the atmosphere. So you're exposed to radiation, but in your job, you may be increasing the amount of exposure because of your medical career, right? So they're estimating that people that work in medicine are really exposed to about 40% more than the average population is. So here's one of the crazy things they used to do. This was in the 1940s. So remember I told you this was like 1890s was when they first really discovered radiation. And then they realized like they could use these radioactive substances, and they could actually then started generating x-rays and exposing it to film. So in the 1940s, they used to have x-ray boxes in shoe stores for people to get their feet x-rayed. It was kind of like a gimmick. So then they would develop it, and you could see their bone, like you could see the bones in their feet with their shoes on, so they could show you that you were actually like the shoes fit correctly. Okay? Like they only did this for about 4 or 5 years. After a while, the Nuclear Regulatory Commission was developed in the 1950s, and they were like, no, because you're being exposed to an awful lot of energy in order to do something that's really not medically necessary. But yeah, that's actually, so you can see like the kid standing on the little platform. So that the x-ray was like in the bottom, and it was like this lead lined box so that they could say, oh, well, no one else was exposed. But they said the boxes were the whole little thing was so heavy because of the lead that a lot of times they just took the lead out because they had to be able to move it around easily. It was like one of the things I was reading. I was like, what? That sounds absolutely ridiculous. But yes, actually was something that went on. Mm-hmm.
So when you say workers doing x-rays, if let's say I'm doing an x-ray and this is the wall, and like
Right.
is this wall gonna protect me if this is
So there's actually, when they build a diagnostic unit, when they build one that's going to hold an x-ray, they actually do have to either lead line the walls, or they have to put a certain amount of concrete layer in the wall. So it can't just be like the metal frame and drywall. It is not. So, and that's so that like the people in the office right behind aren't like slowly releasing, like exposed to x-rays over without knowing. So there's now regulations. So if you work in an x-ray, like if you're a dental hygienist, so the dental hygienists don't stay in the room unless they're like working with a little kid or something, they have to. So if they do, then they gear up and they have their lead line like whole, like torso covering apparatus. But for somebody like a vet tech, they got to stay in the room but for me, like I've going and getting x-rays and stuff, like they trust that I'll stand still. so the radiology tech like positions me and goes, okay, don't move. And she leaves and you hear the little x-ray go, You're exposed, the film now is so sensitive that you are exposed to 100 to 250 times less radiation in an x-ray than you were back in the 70s. When they used to have film they had to develop, that film was not very sensitive. Digital film is so sensitive that the amount that you're exposed to is low. But if you're in a profession where you're having to get x-rayed, where you're standing in the room with the animal like 5-6 times a day, well, then that starts building up. So then that potentially, and your employer is required to then give you a film badge, send it off. And if you come back with more exposure than you should have, then they have to like take you out of x-ray, have someone else do it and give you like a break. okay? Like, so it's sort of like a certain amount over a year. So if 1 month you're high, the next month they're gonna have to limit your use of the x-ray machine so that your numbers come back down, so that you're not putting yourself at risk just through your job. So as exposure goes in, so radiation exposure can have detrimental effects. Long-term exposure is not as bad, like if you have low levels, but longer-term exposure is never as bad. The response is not as bad as what happens if you have short-term. When you think of radiation treatment for cancer therapy, the goal here is to use high energy radiation to damage and destroy rapidly growing cells, right? So that's what radiation does. So patient goes into radiation. Sometimes they will have spot radiation, which means that they only expose a certain part of the body to the radiation. Like say if they had a skin cancer removed and it didn't spread, then they might just do what they call spot treatment. So spot treatment is not going to have as much side effects, but patients that have internal abnormal cells that they found that they have spread, they may choose to use whole body radiation. So more of your body gets exposed to this radiation, and the goal is we want to kill rapidly growing cells because that's a characteristic of cancer cells. Cancer cells grow faster than they should. So if we can destroy these rapidly growing cells, then we can destroy or shrink the tumor or cancer and then have a better chance of removing it, right? So we have chemotherapy and radiation. Those are the two common sort of ways of trying to treat and remove abnormal cells that are growing. So, like I say, the goal is destroy the tumor without destroying you, right? So we want to destroy rapidly growing cells. But now think about in the body what other cells may not be cancer cells, but they're rapidly growing. Okay, blood cells. So side effects, anemia, right? Decrease in red blood cell number. If you decrease white blood cells, that's going to decrease immunity. And that's by decreasing white blood cells. What other cells are rapidly growing? Cells that are constantly being replaced. They're kind of on a cycle. They're not really as, I mean, if a male went through, then probably his sperm count numbers would go down just because they're in this process of development. But think of ones, what are some of the side effects that you see with the patient undergoing cancer treatment? Skin, right? Every 30 days, your epidermis is replaced. So they may develop like a rash, sores, and that's because of skin cells that are damaged. What other side effects do you see? Hair loss, because your hair follicles, your hair grows about 1/2 inch a month. So this damages the root of the hair because those cells in that root are rapidly growing. Any others? Nausea, vomiting, poor nutrient absorption. Why? What's that going to be damaged from? Yeah, your whole GI tract. Your GI tract is replaced every 3 to 5 days. The lining, so the lining in your stomach, lining in your small intestine, they're replaced every 3, even like your tongue, your taste buds. Have you ever like scalded your mouth really bad? Like did that last week. I was like sipping coffee that was cool and I just went and got hot coffee, didn't think about it. Took a big slug. I was like, I was like, ah! Like I felt like the whole roof of my mouth slid off. I was like, oh, my tongue was like, ah. It was all burnt feeling, okay? But 2 days later, I didn't even remember. Then you do it again because your GI tract replaces itself, the lining replaces every 3 to 5 days. So those cells, that is why if that's going to change, now you're going to have the nausea, vomiting, diarrhea. You may have poor nutrient absorption because of irritation and damage to those cells. Those are all these side effects that you typically see for a patient that's undergoing radiation treatment for cancer. And it's just because we're trying to destroy rapidly growing cells, specifically cancer cells, but you can end up affecting normal cells as well. So this is Marie Curie. So she worked with Becquerel. She actually ended up, like, they named curium after her after she died, but she actually discovered radium. So radium was interesting, and she named it that because it glowed in the dark. So she had a vial of uranium that she used as a night light, like a night glowing light. She put it next to her bed, and she died of leukemia. Because it was releasing this radioactive energy. And so then over time, her exposure levels, she had enough exposure that it ended up causing damage to cells, ended up causing abnormal cell growth in her bone marrow, and she ended up with leukemia, which is a cancer of the white blood cells. So that's ended up how she died. And it's all because this was all 1900, they didn't really understand just what this energy was and the potential of this energy. I just thought that was a little amusing. Okay, so when thinking about dosages, so they really measure dosages in what they call millirems. So that's the common one. But when you're talking about stuff like down here, thousands and thousands of millirems in terms of exposure, that's when you're talking about like nuclear radiation, like a nuclear bomb, or having like the nuclear power plant. That leads us to what happened in Chernobyl. So Chernobyl was a nuclear power plant in Russia. It was like up in the Ukraine area, or it's like all in the Siberian, it was in Ukraine. So in 1986, these were a lot of the nuclear power plants. They would get energy by using these radioactive metals that would break down, release energy. That energy would then heat water, generating steam, and then you could use it to generate like a steam generator. So nuclear power plants are pretty great because the nuclear component is always going to be releasing this energy. So uranium is what they call the fuel. So remember, uranium is way down on that bottom row. It's one of the last, I think it might be, well, close to the last of the naturally occurring unstable atoms, because it's in black, not one of the white ones. So when uranium breaks down, it starts off and it breaks down into thorium. So it does alpha decay. And when it does this, it actually releases gamma energy. So it releases that high energy. But then that thorium undergoes beta decay and a couple of other rounds of beta decay and eventually reforms uranium, which then goes through this whole process again. And if you look, do you see this is 238 at the beginning? Down here now it's 234. So that it starts to get a little smaller, but while it's breaking down, it's releasing this energy. So they trap that energy, or they use that energy to heat water, making steam. Steam runs a steam power plant. So that then runs the engines, converts it into electricity. Now they can send electricity to everybody all in that area. So that was like their major power plant. Chernobyl, though, the reactor core, which is where that uranium was, normally it's controlled just how much energy it's released, and they have what they call shields. So they could actually take the uranium, slide it into this thick lead shield, and that would like shield it so that it didn't heat the water too much. Well, they hadn't done the maintenance on it, and so it wasn't working correctly. So they decided to run a full test and just shut the shields off completely, stopped the water circulators. And so what happened was so much energy was released into the water boiled. It boiled, it converted into steam very rapidly, and that literally blew the top off of the nuclear power plant. So when it did that, it ended up spitting, throwing into the atmosphere 2 unstable isotopes, cesium-137 and iodine-131. So that was actually dumped, and it was actually measured in France. So it was measured 1,500 miles away. They started measuring higher than normal levels of radiation. So they were like, something happened. And because Russia was like, no, everything's fine. Yeah. It's kind of like China with COVID. No. No one's gotten sick over here. We're fine. Yeah. So prior to 1986, about 1 per million people would get thyroid cancer. So thyroid cancer, remember, your thyroid gland is that little gland that's in the neck, and it's the only gland in your body that uses iodine. After, in 2003, they're up to about 60. So it increased thyroid cancer about 60-fold from its normal. And that is because iodine-131 is an unstable isotope of iodine. So it got into the air, it got into the water, it ended up being ingested, goes to the thyroid, and it's releasing radiation, releasing energy that then caused abnormal cell growth of the thyroid and led to these numbers increasing. They had to move out, like within a week, they evacuated about 350,000 people out of that area. Well, yeah, they were like, no, nothing happened, it's fine. So they still don't really ever have like the true number of people that like died directly, because some people had to go in and like try to like control the fire. Firefighters responded. Then they had to go in and they were trying to like dump concrete to close off the top of this open reactor. And so they're like, the Russian government's like, not very many people died. I'm like, I find that very hard to believe that not very many people died, because that is some serious amount of energy from just this open reactor core. So even now, this is still, it's really odd. Like, they've gone back to the area near Chernobyl, like the towns, and they're just like apartment buildings, houses, high rises, and no one lives there. They're just like emptied. Like, and no one's moved back. They still are kind of keep people out of that area. They eventually covered that entire thing over with concrete. Like, it's a big dome. They put like they call it a sarcophagus. They put a big dome, but there's still a question if it's leaching into the ground. But the Russian government says no, it's fine. They don't really like to answer about that stuff. All right, well, I guess I'm going to quit there, which is okay, because we've talked about protons, neutrons, and electrons. We talked about how to calculate them. We've talked about the radioactive form. So like if you have that exam review, okay, the only thing really we haven't done, we went all the way down. We didn't do half-life, okay, and then treatment versus diagnosis. So kind of like those last ones. We didn't talk about it in class. It's not going to be on your exam, okay? So kind of like the last little section. That's really all that we haven't covered. So and make sure that you go through everything else. You should be all set. So it'll be Monday night in here. I will be down if you want to start, because sometimes students like to have extra time or whatever. I will be in here by 5. So if you would like to start a little early so you don't feel